So what we have done, we are going to see it in some, we have taken a historical review of the whatever early attempts. So now we are going to see it a bit more in a very specific sense, how Dirac equation, its covariant form, and how so the topics we are going to sort of review some of the topics of relativistic quantum theory. So what we are going to do, जो ये हमारे पास this book by Brill, we are going to just take a glance over chapter 1, 2, 3, 4 and 5. So as a beginning, so we'll just try to see the topics covered in these chapters, which will just motivate us further in our study of quantum field theory. So the topics given here is how we can formulate relativistic quantum theory in that sense. So formulation of relativistic quantum theory. So in some sense what we are going to do is we are going to see the way we have postulates of quantum mechanics. In the same way we can have postulates of relativistic quantum mechanics theory. Modulo that fact that the idea of Lorentz invariance, is there, very much there. Means the limits of special theory of relativity. Limits of special theory of relativity are there. अब ये हमारे पास है, so we have to study mathematically. We have to study mathematically. We have to study relativity in Lorentz covariant form. अब Lorentz covariant, Lorentz you know, it's just the upper bound of special theory of relativity is what I should say respected. But it should also be covariant, which will just come what we mean by covariant in the specific sense. So briefly, if there are, if just like we just formulate some minimum postulates of quantum mechanics, in the same we can have some minimum postulates of relativistic quantum mechanics. उसको base बना के फिर हम we are going to just study Dirac equation, उसकी covariant form, poles, a lot of other things. तो आप उसकी जो फर्स्ट पोस्टुलेट ये है, फॉर एग्जांपल फॉर ए गिवन सिस्टम, गिवन फिजिकल सिस्टम, there exists a state function phi. So that summarizes all we can know about the system. So वहाँ पर state function psi है, psi contains information. You can say state function phi may exist. So जिस तरह हमारे पास अब ये है कि we will just begin with one particle theory. And it's like we can have one particle states, two particle states, n particle states. For one particle states, what I should say, which has a coordinate realization of that state function, which we define this way. So the wave function जो हमारे पास है psi, so it will be qi si t, or psi may be having functions of q, s and t. So if you remember, normally हम जो function psi है ना, either it's a coordinate variable or it's a time variable in quantum mechanics. But here you can also additively take spin also in the state, relatives to quantum state. Spin as a property can also be included in this state function psi in that sense. And such that, for example, and this maybe this spin is intrinsically quantum mechanic. Fine. अब ये है कि जो हमारे पास ये है so in those psi may not have any direct physical interpretation, but you can write psi as psi of this is q1, qn, s1, sn. So since जिस तरह हमारे पास वहाँ probability ये होती है, we take square of the probability. So it should be some positive definite. So in the same way we should say the interpretation. Psi square जो इसका ये होगा ना, which is also contains spin as one of the parameters. इसका जो modulus होगा it will be positive definite. Such that probability will be 1. क्योंकि हम वहाँ define करते हैं ना psi in terms of complex conjugate. So that's why उसका modulus आएगा 1 और positive का. That's you see this postulate 1. Postulate 2 means every physical observable is represented by linear Hermitian operator. In particular अगर हमारे पास canonical momentum pi है, तो जो उसकी operator correspondence होगी pi can be written as h by a prime. So we can every physical observable is represented by linear Hermitian operator. So in particular, if you have a momentum operator can be written in terms of, if you want to write it in terms of coordinates. H by r and d by d. So it corresponds position and momentum, space, and energy and time. So the way you might have studied in quantum mechanics. A third postulate है a physical system is in an eigenstate of operator rho if rho of phi of n will be equivalent to where if you remember phi n क्या है, it's what covers it's the eigenstate of the operator. This will give a eigenvalue. So the way we study eigenvalue problem, eigenstate and for a particular eigen operator operating on this eigenstate, this will give us eigenvalue. So the functional correspondence between an operator acting on a particular eigenstate, which will give us a particular eigenvalue. That's it. अब सिर्फ इसमें फर्क यहाँ पर ये है कि जो हमारे पास phi है, it may not necessarily be two parameters. We can also have spin as a property also here. So you can have जो हमारे पास rho है, phi can be q s t. It will be omega n psi n q s. Sorry, sign. So in coordinate realization, we can say it's equivalent to this. So if it's not pi, it's sine. You can have omega and sine in terms of q s and t. in that sense. So these are three postulates. So we can, जिस तरह हम वहाँ पर quantum mechanics के टेस्ट करते हैं, तो how we can what I should say normalize a given state, and what are orthonormal states or orthogonal states हैं. In the same way, the expansion postulate जो हमारे पास है, it states that the expansion postulate states that अगर हमारे पास कोई भी arbitrary wave function होगी, arbitrary wave function psi function or a state function, whatever that is, for a physical system, can be expanded in complete orthonormal set of eigenfunctions psi. So you can expand it like that. So what we are basically doing relativistic quantum mechanics. So relativistic quantum mechanics में we are trying to study the postulates of relativistic quantum mechanics. So the postulates of quantum mechanics, we have the way we have postulates of quantum mechanics, we can also in the same way summarize relativistic quantum mechanics postulates. And we have gone through 1, 2, 3, and the fourth one is this: how we can expand a given state. So for example, psi can be written as so if you want to write psi as a complete, you can write it as a summation of this psi n, है ना? A1 psi 1, A2 psi 2. उनका फिर summation फिर at the end you give the probability that will be equal to 1 on the right hand side, है ना? The evolution of quantum mechanics में हम क्या कहते हैं? The evolution of wave function in space, which moves from point to point, which is being operated upon by the operators जो भी हमारे पास, and उसका फिर at the end summation निकाल देना ऐसे psi star psi is equal to 1, a condition comes out to be, and means that probability volume जो भी होगा it will come out to be. But जो individual psi है ना, psi can be जिस तरह आप हमारे पास कोई भी वेक्टर क्वांटिटी है ना, उसके डिफरेंट कंपोनेंट्स हैं. At the end जब वेक्टर रेजोल्यूशन हम करते हैं, वेक्टर we add those components and get psi. Okay? Psi. So in the same way we can see psi is the summation. Those components of the psi which will at the end they are going to sum up. This is the same. So if we have orthonormality condition, which can be written as orthonormality condition हमारे पास है d2n. अब इसमें फर्क ये है कि we have also here the spin variable, है ना? Normally quantum mechanics में हमारे पास the space derivative space में कैसा state function evolve करेगा? Time. यहाँ you can also take as a quantity. So you can say that it will come out. This is psi n. This is psi n. it will come out to be delta m, है ना? M is equal to n or m not equal to n. For m is equal to n, it will be 1. For so we are trying to see relativistic quantum mechanics. The way we when we still begin the course of quantum mechanics, हम क्या कहते हैं? What are the postulates of quantum mechanics? तो उस वक्त आपको समझ नहीं आता था ये psi क्या हो गया, psi star, psi is 1, normalization, है ना? Later once you apply things. But here we are going to we have to study quantum field theory. Before studying quantum field theory, we should have a covariant relativistic Lorentz equation, Lorentz invariant relativistic equation. उस हिसाब से हम quantum mechanics को at high energies जो particles when move, तो they also satisfy principles of special theory of relativity. तो हमको special theory of principle relativity के principles को incorporate करना है. So now we are going to reformulate the postulates not of quantum mechanics, postulates of relativistic quantum mechanics. And उसमें फिर not only variables, space, and we can also have s as variable. We have 1, 2, 3, 4, and this is 4. And the fifth postulate is एवरेज ऑफ द मेजरमेंट. हम जिस तरह लेते हैं ना फ्रीक्वेंसी सम एंसेम्बल, टेक एवरेज ऑफ द एंसेम्बल, है ना, एंड एवरेज ओवर इट ओवर द होल स्पेस. सो इन द सेम वे जो अगर फॉर एग्जांपल अगर कोई भी सिस्टम डिफाइन होता है psi फॉर एग्जांपल, इफ यू जस्ट फॉलो द बुक, इट्स रिटन एज a n psi n, एंड जो इसका ये है इट्स रिटन एज ओमेगा n psi n. This is the individual wave function psi, these two different components. This is basically operating on this that this will give the particular eigenvalue. अब ये है कि एवरेज ऑफ द मेजरमेंट्स जिस तरह हमारे पास है ना प्रोबेबिलिटी psi star is equal to psi star is equal to 1, या हम ऐसे कहते हैं मॉडुलस ऑफ psi star is equal to, क्योंकि हमने psi को इन टर्म्स ऑफ कॉम्प्लेक्स कंजुगेट डिफाइन किया था वेव फंक्शन को वहां पर, है ना, तभी हमारे पास probability will always come to be positive definite. So now you have to apply the same thing here also. So what we are going to say in that sense, the average of the measurements of observable rho on identically prepared systems. So this is for our simplicity. Some classical mechanics में ना particles of the same mass लेते हैं that. So for identically prepared system, उसका जिस तरह ensemble है ना, उसका evolution देखते हैं. How इसका ये so how they will evolve in that space. So that will be given as हम expectation value निकालेंगे या so average value निकालेंगे. It will be sort of Q1 S P root epsilon Q1 S E dQ1 dQn. So it will be an square omega n. It will be the way we have probability will be this. अब ये एक कहाँ से आया? You can see it. We have defined it like this. है ना? Psi का psi star आएगा. Psi star इसको multiply करो psi star के साथ, है ना? VAN psi star. Multiply both sides. Psi square is equal to AN square. Omega and other different modes. Psi 1, psi 2, psi 3, so on and so forth. Now the sixth postulate is, for example, so any time development of physical system is expressed by Schrödinger equation. Iota h d psi by dt is h psi, where h is linear Hermitian. So it has no explicit time dependence for a closed system. For a तो dh by dt क्या आएगा इसका बस? It will come out to 0 because no energy goes outside the system. Within the system, you can define this. If it's a Hermitian operator for a closed system, it can be defined this thing. So there is a particular way also to show the conservation. We can also arrive at a conservation law from this. कैसे? So इसको मैं आपके लिए exercise रखूँगा. या still So if you have d by dt of psi star psi dq1 sigma h dq1 h psi star psi minus psi star, so it will come out to be 0. So how it will come out to be 0, Suhail? So you can see it from here. So इसको psi star करो एक बार, ठीक है? दो आएगा psi star d psi by dt plus psi star d psi by dt plus h psi. So you just do it. So it's an exercise of showing that this is also equal to this. So it's an homework. Okay, just think about it. So and how we can restate this for closed systems, we can write it like this way also. So this is our how we can to summarize करने के लिए what the way we have postulates of quantum mechanics, we also can have postulates of relativistic quantum mechanics. ठीक है. अब यह है कि कोई भी फिजिसिस्ट या कोई भी साइंटिस्ट जो होता है, जो फिजिकल जो सिस्टम हमारे पास मेजरेबल सिस्टम है, हाउ कैन एक्सप्लेन इट फ्रॉम द फर्स्ट प्रिंसिपल्स. समटाइम्स वी कैन जस्ट रिड्यूस दीज पोस्टुलेट्स और ऐड सम पोस्टुलेट्स, है ना. टू बिगिन विद वी कैन स्टार्ट विद दीज पोस्टुलेट्स एंड देन वी विल जस्ट कंटिन्यू. ओके.